we found in this very next step, this is correct, right? This is your sheet. This is where we left off, okay? In this next step, I circled the sine squared because I was trying to point out that the right-hand side has no cosines involved at all. So our goal should be, how are we going to get rid of this sine so that this is all in terms of cosine? So this is where your identity would come in, and sine squared can be replaced with what? What's an equivalent expression for sine squared? Okay, you're using that one, right? So this is another option, but again, if we use that option, and we probably couldn't, we could get away with it, but if we use that option, we're going to be faced with a cosine of 2 theta again, so we're going to be faced with having to use a double angle again, because we don't have cosines of 2 thetas in our answer. So this is where it becomes tricky, because you have to try to have a little bit of foresight and know what the best choice is. I'm saying keep it basic. Use your Pythagorean identity. Sine squared plus cosine squared equals 1, which means sine squared can be replaced with 1 minus cosine squared. And then on that binomial, I can now distribute negative 3 cosine. Even though it's written in that order, does everyone buy that I'm really just distributing negative 3 cosine theta to the set of parentheses? Good, John? Okay. So cosine cubed theta is still there, and I'm distributing negative 3 cosine theta to 1, so it'll be minus 3 cosine theta. And I'm distributing negative 3 cosine theta to negative cosine squared. So the double negative is going to make that a positive 3 cosine cubed. And then combine like terms. We have 1 cosine cubed plus 3 cosine cubed is 4 cosine cubed minus 3 cosine theta, and I'm done. So one thing that, again, might have been worth realizing way back here when whoever, I don't know, maybe it was me, I don't remember, when we were deciding which of the 3 options to use for the cosine of 2 theta. Of our 3 options, one involves a cosine squared and a sine squared. One involves just cosine squared, and one involves just sine squared. Based on where we were trying to go, we were trying to get the left side to match the right side, and the right side was all cosines. It probably would have been wiser to use the second one, because that one's all cosines already. Again, it doesn't make or break it. You can usually still iron it out, but you would find it simpler, I think, if you had done it that way. So here's this same proof done in the book. So they, like we did, they split up the 3 theta into 2 theta plus theta. They use their sum of cosines formula. And they kind of show it to you. It's nice, like, because it's color-coded. They show that they're taking the cosine of 2 theta out and replacing it with that version. And they're taking the sine of 2 theta out and replacing it with that version. And in doing that, they're also distributing at the same time. Minus 2 sine theta, cosine theta, sine theta. Oh, no, they didn't distribute yet. So they just substituted it out. Then they distributed. So you got the cosine being distributed to 2 cosine cubed minus cosine. And then they just did their sine times sine into a sine squared. And then, again, because we don't want sines, we can take out that sine squared with 1 minus cosine squared, distribute, clean it up, and we get it. So done differently. They chose a different double angle for the cosine of 2 theta, but it all works out. Okay? Some ways are just going to be easier than others. So when it comes time to making a decision, try to look at where you're trying to go, and if that can offer you any guidance, and it might not be a guarantee either, but it sometimes will help to just know where your end result is. Okie doke? Okay. On the next one, writing in an equivalent expression for cosine to the fourth power of x that does not contain powers of trig functions greater than 1. In other words, we can't have any exponents. No powers on the trig functions. Okay? This is where your power reducing comes in. I have to say, of all the formulas on the sheet, I think these are used, the sine squared, cosine squared, and tan squared power reducing are used probably the least, just being honest. Because lots of times for sine squared, like what I just said to Abby, we're not going to plug that in an identity only to then have to replace the cosine double angle as well. It just creates too many substitutions. When it's much easier just to take out a sine squared and replace it with 1 minus cosine squared like we did. So these aren't used a lot in identities at all. I would probably try, if I were you, to stay away from them. But specifically when they ask you to reduce the power. So first of all, this is to the fourth power, yet our rule refers to cosine squared. So the first thing I'm going to do is I'm going to rewrite this as the cosine squared of x squared. And then this cosine squared of x section is where I'm going to bring this into the mix. So you can either write it exactly like that, or you could distribute your 1/2 if you wanted. I think I might distribute my 1/2. And so I've gotten rid of one of the exponents by doing that. I still have a power there, though. So I'm going to FOIL this out. So I'll really expand it so I don't lose anybody. I'm taking this binomial and I'm multiplying it by itself. That'll be plus a fourth cosine theta plus another fourth cosine of 2 theta. So that'll be a fourth plus a fourth, which is a 1/2. And then my last will be a 1/2 times a 1/2, which is a fourth cosine squared of 2 theta. So again, that square didn't go anywhere just yet, but it's about to, because I'm going to use my power reducing again on just that portion. Now this section is a little bit trickier because this is cosine squared of theta on my reference sheet. This is cosine squared of 2 theta. So wherever there's a theta over here, I need to make a 2 theta. So what's going to happen here where there's a 2 and that's a 2 theta? It's going to turn it into a 4 theta, okay? So this particular section of it, there's the 1/4, and the cosine squared of my angle is going to become a 1/2 of 1 plus cosine of 2 times the angle I'm dealing with. So 2 times 2 theta is 4 theta. And then the beginnings I'm not touching. So on that last term, I can really just distribute a 1/8, 1/4 times 1/2 times a binomial. That's just going to be 1/8 distributed in. So 1/4 plus 1/2 cosine of 2 theta plus 1/8 plus 1/8 cosine of 4 theta. And then you can combine 1/8 with 2/8 technically and make that 3/8. just to combine like terms. But then we can be done. There is definitely an opportunity to use a double angle, but it doesn't tell us that we have to simplify this completely. It just says rewrite it so that there's no powers. And so we don't have any powers. There's no need to use the cosine of 2 theta. In fact, we probably wouldn't want to, right? Because if you use the cosine of 2 theta, you're then going to reinsert squares on trig functions, and it specifically tells you can't have those. So that would even be foolish to do that and reinsert sine squares and cosine squares. Okie doke. So those specifically ask you to sometimes power reduce, and that's where those formulas will come in. Okay? The next one, you're sitting on a test, you have the question, find the exact value of the cosine of 112.5, which of course we don't know, right? So there's got to be a formula, and it's usually going to be a double angle if that's double something that we know, or a half angle if that's half of something that we know. So what would you have to double in order to get 112.5? 56.25. And do we know cosine, sines, or tangents of that? No. So it's probably not a double angle. We're not doubling anything to get to 112.5. What would we have to cut in half to get to 112.5? Andrew? 225. So we could think of this as that, as 225 divided by 2. Now, do you know the cosine of 225? Not immediately, because it's not one of our 0, 30, 45, 60s, or 90s, but it has a reference angle of that. So if we had to figure out the cosine of 225, we could do it, because what quadrant is it in? Third. And what's the reference angle? 45. So if we're asked to find the sine, cosine, or tangent of 225, yes, we can absolutely do it based on our 45 values that we know. So go to your reference sheet, find your half angle formulas right here. This is cosine. Okay? So all of your half angle formulas are preceded by a plus or minus sign. That's because you have to decide what quadrant this is in. At the end of the day here, we're finding the cosine of 112.5. So even though 225 is in the third quadrant, where's 112.5? Aiden? The second. So whatever value this is, if we're in the second quadrant, we're taking the cosine of it. Is it plus or minus? Minus, right? Cosine is negative there. Keep in mind on that's the tricky thing here. You're choosing your plus or minus based on the original angle, not based on the 225. Is that clear? The positive, negative nature of the cosine of 225 will come into play within the formula. So we've chosen the negative for this particular problem. It's the square root of 1 plus the cosine of 225, right? Our theta is 225 over 2. And then we're just going to simplify that. So negative square root of 1 plus something over 2. Now, the cosine of 225, reference angle of 45. What is the cosine of 45? Root 2 over 2. And because 225 is in the third quadrant, is the cosine of it plus or minus? Negative. So negative root 2 over 2. Now, cleaning this up is another issue because we have complex fractions, right? This is where I really, well, I don't really care that much if you can keep track of it. But because those of you who could insist on getting a common denominator between these two, then doing the subtraction, then keeping, changing, flipping, that's just a lot of mini steps within a expression that's underneath radicals and with radicals involved. To clear this complex fraction, the mini denominator is 2. I say you just multiply by 2 over 2. And your complex fraction will be gone. So we have negative square root. On the numerator, distribute your 2, you get 2 minus root 2 all over 4. On a multiple choice, you might see that as your final answer. Or, when you're taking the square root of a fraction, you're technically taking the square root of the numerator and the square root of the denominator, which looks like a very plausible thing here because the square root of the denominator is what? Just the whole number 2. So you could get rid of that, and this might also be a way in which your final answer is expressed. I'm sure I pulled this from the textbook, not that it's the same thing, but that is the way they leave their final answer. Negative square root of 2 minus root 2 over 2. As far as a radical under a radical, there's really not much we can do about that. Questions? Okay, so in a case like this, and was it on the front? No. I'm trying to think where I'm half angle. The more I reflect on this, I feel like we don't really use the double angle ones much to evaluate cosines of functions or cosines of angles. We use the half angles much. We don't use the double angles much for that. Because the only angles we know are 0 degrees, 30 degrees, 45, 60s, and 90s. And if we were to double any of those, doubling 0 is still 0, doubling 30 is still 60, doubling 45 is 90, doubling 60 is 120, and doubling 90 is 1. We know those values anyway. So we wouldn't see find the sine of 180 and say to ourselves, use the double angle formula of 2 times 90. There would just be no need to do that. So I don't think we use the double angle much for evaluating sines and cosine values, simply because we'll already know those. But the half angle is really where we'll use those to kind of evaluate angles. The double angle formulas, I will say, I think are mostly used for identities and for the type of problems you saw last night with drawing your pictures in a certain quadrant and actually just answering what that would be. Okay? So just trying to give you some compartmentalizing, which formulas are used. And that's what tends to happen. Okay, so do you have your reference sheets out? If you don't, get them out. I want you to work on this lower left verification. Raise your hand if you're done with the first one. Raise your hand if you're stuck on the first one. Just note that this wasn't exactly the same. It's the same structure. If angle goes back to there, your angle is 2 theta goes back to there. Good. Pretty good on that? So I don't even follow. What happens if people stop and say, how does the top come down? Okay, so I need you to show that. This is 1, this is minus, and then this is that. This is 1 minus, this is there. And so show, even if you did that right, once you did that, if you're not showing it, I'm not going to sit there and try to figure it out. So make sure you show yourself. Who else? That last one was, we need to go look at it. So when I say who else, you sit there and you say nothing? No, that's not how my room operates. We are an open book here. Otherwise, rich get richer and I'll get more name. Yes, advocate. So you click the bottom, right? So you handle this stuff with it. You never did anything. And you have a choice to make. Oh, you want to change this based on two data outputs. So what choice you pick? If you were any forfeit, you were to guess as to what you think might work out in each of this, I'll tell you that a lot of your classmates did good predicting how it worked out, but if you have any idea, if you're good with that bottom left, try the bottom right. So now what would you do? Okay, what do you next? What needs more simplifying, the top or the bottom? Okay, so what does that mean? I'm not talking about substituting anything out. I'm talking about just flat out. That's not, I mean, I appreciate that's what we just go, but yeah. So that. Well, bottom left. You're all good. The bottom left. I like it. Trust you. I don't know if someone pulled it out on me. That's good. 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 How about bottom right? Raise your hand if you already got the bottom right one done. Is it easier? Oh, what? Doing second bottom right? So you started with that. Did he finish it out? You're just one though. No, it's not negative 1 times, it's 1 minus that. 1 still there, and you take the 2 from there. There you go. Nothing is cancel off with this 2. Okay, so she's got nice handwriting. You got the bottom right? Okay. So this is what I did on my bottom left. I used, and I just kind of somewhat blindly guessed for the cosine of 2 theta. Since I knew it was 1 minus that, I used the 1 minus 2 sine squared so that my 1 minus 1 would just be gone. Does that make sense? A lot of you didn't. A lot of you actually used the, what did you use? Right, and then your 1 minus cosine squared, you guys made sine squared. So we all ended up eventually with 2 sine squared theta. Then your 2's cancels, your sines cancel, leaving only 1 up top. Sine over cosine is tangent. I'm just going to look at Bailey's here. Like, the only trouble, Bailey, I have with this is, like, you did the same thing I did, I'm pretty sure, but you're not showing it. Like, I'm not actually seeing what it is that you've replaced that with. You just went right to a simplified. You, like, replaced it and simplified it all in your head or on paper and then erased it and have what it became.
No, I just, like, kind of use, if you like, you know what I'm saying, like, if you subtracted it.
But I have to first figure out what are you subtracting. I have to kind of guess which one you must have used, right? And that's what I don't like to have to do. So if you're substituting something out, leave everything else the same and just take it out and change it and then actually show all that work. Just for that communication piece. But she obviously did it right. And here's her other one. So for this one, on the reference sheet, she used the tan of alpha over 2. And there are 3 versions of that. 1, 2, 3. The plus minus one is tough to use because in a proof you don't know whether to use the plus or minus because you don't know what angle you're dealing with. She used the 1 minus cosine over sine, and then she split it up, 1 over sine minus cosine over sine, and she was done. Okie doke? I don't know why I didn't write these 2 on the top of your sheet. So if you were just limiting yourself to these, that one would have been difficult. Okay, but it was easy if you saw those 2. By the way, the only person that did this one differently than the double angles is Nate. And what he did was he looked at this same one, saw 1 minus cosine of something over the sine of something. Everybody see the structure being the same? So he really took that expression and went backwards to this one. So this expression, the alpha has a 2 theta in it. So when you go back here, it's just the tangent of 2 theta over 2, and 2 theta over 2 is just tangent of theta. Sometimes I'll exclude you from using those because they can be that easy and it eliminates the purpose of a proof. But your homework for tonight, day 2, same page, 23 through 81, 1s, 3s, and 5s. So we did the 1 through 21. Now this is all your identities to start anyway. So 1s, 3s, and 5s. There you go, Bailey. Yeah. You too, thank you.